when you have an equation, you should check algebraically for whether there is a particular type of symmetry or not. So, for every point A comma B on a graph, if there's x-axis symmetry, let me write in symmetry here. I'm going to abbreviate symmetry as SYMM. Then, if there's x-axis symmetry, you get a change in the y-coordinate by switching the sign. Here's a particular example, and here's what we have in general. If there's y-axis symmetry, the coordinate that changes sign is the x-coordinate. So notice that reversal. Any point on the graph, change the sign of the y-coordinate. That point is also on the graph. X-axis symmetry, change the sign of y. Y-axis symmetry, change the sign of x. For every point on the graph, if there is y-axis symmetry, then negative a comma b is also on the graph. And if there's origin symmetry, then you change both signs. For every point a comma b, if there's origin symmetry, then negative a, negative b is also on the graph. So to test this one, y squared equals x plus 36. Something that jumps out at me about this is we have our variable y. It's not isolated, but it's only part of being squared. That's on one side. And if I change the sign of y, squaring y versus squaring negative y times negative y, the negatives would cancel out, and we would be back to what we started with. The fact that we changed the sign of y and we're back to what we started with is telling me that we have x-axis symmetry. Whereas if we try to change the sign of x, to check for y-axis symmetry, then that would give us this. It does not look exactly the same as the original equation. So if you're wondering, is there some way of rewriting this to see that really we've got the same equation? Well, if there were, then since y squared is isolated in both of them, that would have to mean x plus 36 would equal negative x plus 36. And that would give us, by combining like terms, negative 2x equals 0, so x equals 0. That's actually telling us the only place where, if you change the sign of x, that you get the same point. Well, a reflection over the y-axis. Well, in that case, change the sign of x. 0 versus negative 0. That's still 0. that's actually going to sit because x is 0 on the y-axis. And any other point on this graph, if you change the sign of x, you're not going to find another point on that graph with the same y-coordinate, and the x-coordinates are just negatives of each other. So the same thing's going to happen with origin symmetry. There's no x-axis symmetry. When we check for origin symmetry, changing the sign of both x and y, and we already saw what happened when we squared a negative y. It's the same as y squared. At this point, we're back to the same problem we had right here. So we're not going to be able to rewrite this and make it look exactly the same as the equation we started with. There's no origin symmetry. We have only shown that there is x-axis symmetry. It wants intercepts first. It's actually pretty straightforward to do. Y-intercept of 0, 36. 36. Whereas if we put in 0 for y, you'd have x plus 36 equals 0. So that would mean that x is negative 36 when y is 0. Okay, let's see here. What did I do wrong? 0 for x. 0 plus 36 is 36, but that's y squared. Okay, so we take the square root, plus or minus, to get what y is. My x-intercept, on the other hand, should be fine. And then we're asked, is there x-axis symmetry? That is what we found by changing only the sign of y. The other two types, we will be answering no. And every time, my lab agreed. That's it for now. Hopefully this has helped. If it has, please like the videos, subscribe to the channel, and if you know someone else studying some of the same mathematics and they need additional resources for help, send these their way. Share the videos. Thanks, and I'll see you in the next one.